welcome. So today the last session is handled by Dr. Jerrin Joy Varughese. He is an assistant professor at Dayananda Sagar University and he has completed his PhD from VIT Vellore. So without much formal introduction, I welcome Dr. Jerrin Joy Varughese to deliver the session. Thank you, sir. Welcome.
Okay, thank you, sir, for the warm welcome. I first of all thank the management of Sripati Institute of Management and Technology for organizing such a wonderful FDP, Material Science in the era of AI and recent trends, and definitely the Department of Mechanical Engineering for hosting this event. And I want to thank Mr. Romanath P, Assistant Professor of Mechanical Engineering Department, and Mr. Jyotish Manu, Assistant Professor of Mechanical Engineering, and Dr. Ramesh Phoebe. He was the first person actually who invited me to this event. And I thank the convener, Mr. Sridhar Temke, Associate Professor, HOD in charge of Department of Mechanical Engineering, and the Principal and Chairperson, Dr. S.P. Subramaniam. And I welcome you all, where I would like to discuss on ultrasonication assisted exfoliation of two-dimensional nanomaterials. Umnath sir, am I audible? And whether the screen is clear to everyone?
Yes, sir. You are audible and the screen is visible.
Okay, thank you. So let me first go to the first title or the first topic. It is nothing but nanomaterials. So yes, I know that we are all faculties and we all know what is nanoparticles. There is no need of emphasizing more onto this nanoparticle. But I thought of just mentioning, what is nanoparticle, and then later go to, the specific two-dimensional nanoparticles. Yes, as we all know, nanoparticles are those materials whose any one of the nano or any one of the dimensions are less than 100 nanometer. Okay, so our materials or particles are being classified based on that, like zero-dimensional materials is there, one-dimensional material is there, graphene, sorry, two-dimensional is there, and three-dimensional materials are there. And you can see that zero-dimensional materials are those in which whose dimensionality in all axes, X, Y, and Z, will be less than definitely 100 nanometer. And in case of one or the one-dimensional material, it's one of the dimensions will be more than 100 nanometer. And when it comes to the two-dimensional, it's lateral surfaces or the so-called X and Y or Y, Z, or any two dimensions will be more than 100 nanometer, where it's one axis will be, or one dimension along one axis will be less than 100 nanometer. And then comes the bulk material, which is the larger piece or the larger chunk among these the so-called nanoparticles. The reason why I thought of taking about this two-dimensional nanomaterials is that, when it comes to zero-dimensional material, quantum dot, synthesizing quantum dots are most difficult thing, because you need to control the mechanism. You need to make sure that it is being brought under the 20 nanometer, the 10 nanometer, and a lot of research is being carried out in this quantum dot sections. And nanowires, that the CNT, carbon nanotubes, those comes under the one-dimensional material. And my focus is onto the two-dimensional materials, where one dimension is less than 100 nanometer. And here you can see that it's a graphene sheet and whose thickness is well below 100 nanometer. And why two-dimensional material gain an importance is that it has got a high surface to volume ratio. Okay, so that's the reason why we are using this two-dimensional materials. Then, and if you are using this two-dimensional materials, so where you are going to use it? See, in most of the cases, when it comes to the polymer nanocomposites or any metrics like metals or anywhere you are going to use, these nanomaterials do have a different kind of influences. So when you are using these nanoparticles, for example, graphene or HBN or MXene, these will improve the mechanical, thermal, optical, and electronic properties. So, and the reason is that these do have a greater surface areas. Okay, if you take a look onto this graphene sheet, you can see that more of the surface area can be seen, right? So comparing to its volume or comparing to its thickness, it do have a greater lateral area which can be utilized for the further process. So these are the commonly used two-dimensional nanomaterials, which has been employed for several, research purposes or several applications. You can see graphene, HBN, MOS2, molybdenum disulfide, then tungsten disulfide, MXene, and black phosphorus. And you can see that each nanoparticle is having, different properties. Like graphene is a wonderful nanoparticle, which do have better thermal as well as electrical property. So it is being mostly utilized for the applications like electronics based of applications, where HBN, where my research was mostly into HBN. The reason why I chose HBN was that even though it do have a relatively high thermal conductivity, its electrical conductivity is too low. It is an electrical insulator. So you can use this material as a perfect, substitute where you need to have this thermal conductivity or where you need to utilize the thermal conductivity without being affecting or without being influenced by the electrical parameters. So mostly into thermal management. MOS2, you can see that its property is lying in semiconductor areas where it can be utilized as sensors, tungsten disulfide as optoelectronic application. So likewise, you can use this 2D, two-dimensional nano materials. So why I want to show this slide is that, choosing or if you're picking this particular nanoparticles, you can apply these nanoparticles in various applications, what I have mentioned over here. Okay, so at the bottom, you can see several structures of these materials. See, one of the most what attracting thing is that you can see that the graphene and HBN is having the hexagonal crystal structure. Okay, but at the same time, even though their atoms are so similarly aligned or similarly packed, they do have differences in electrical conductivity. So you cannot simply say that by seeing the crystal structure or atomic arrangement, one particular material is having a kind of characteristics, or they may share the same kind of characteristics. So there, that may go on and on, that may changes. So this is something related to exfoliation. See, exfoliation is the word I want to stress a lot because, two-dimensional material, as I said, it is actually a material that will give you high surface area. You take a look onto this bulk layered crystal. Okay, so whatever material you are going to take, for example, graphene or HBN, MOS2, these material do have a tendency to pile up like this. Pile up like this. Here you can see that 10 plies of nanoparticles are being plied together to form a bulk crystal. You know, this material cannot be directly used for further polymer nanocomposite preparation or for any other applications because the reason is that you are not actually fully utilizing the surface area of what this bulk material. So we indeed need to segregate these particles, segregate these layers, and make it more useful for what your application or for your further synthesis. So there comes our, the point exfoliation. Okay, so exfoliation is nothing but here, what you're going to do is that you are just segregating each layers. How you can segregate it? Segregation can be done by inputting energies. Okay, so by inputting energy, it could be thermal energy, it could be chemical energy, it could be mechanical energy. In any form, you just incident or you just given energy and you just make sure that or you just make these layers separate so that each layer will act as a reinforcement material, each layer will act as a thermal conducting material, each layer will act as a property enhancing material. So you are actually what you are going to do is that you are actually improving the surface area and making it perfect fit for the application. So that is called exfoliation or layering of, or you are segregating the bulk crystal or bulk layered crystals. Why you are doing this? To provide higher surface area, better reinforcement that will improve the dispersion. Definitely that will lead to enhanced properties. Okay. Now, two-dimensional nanomaterials, how you can prepare it. We do have two kind of major approaches, bottom-up approaches and top-down approaches. Bottom-up approaches and top-down approaches is one in which you can actually produce this two-dimensional material. And I'll tell you, in bottom-up approaches, there we use reagents or precursors are taken, and several chemical reactions will carry out, or you are just building the 2D materials atom by atom. Okay, so if you take a look onto CVD, what happens is that in a chamber, you will first allow one reagent to get inside, and then you will allow another gas reagent. And chemical reactions will happen, and it is allowed to actually fall over a particular substrate. And that's how growing of that particular deposit over that substrate will give you the growth of what two-dimensional nanomaterial. So you are adding those materials. So it is building up. Okay, that is what is known as bottom-up approach. Likewise, in PVD, physical vapor deposition, there what you going to do is you are not actually using any reagents, and you are not actually what you call chemical reactions are not happening. What it is happening is that there the raw materials is being heated and the vapor has been formed, and that vapor is allowed to fall over a substrate, and that particular substrate over that particular substrate deposit is formed, and that deposit is nothing but the two-dimensional material. So there happens what atom by atom deposition. Okay, but and hydrothermal, I think you guys have seen Arun Sam's allowed you to build one 2D, two-dimensional material. So there also the same thing happens, atom by atom deposition. But when it comes to top-down approach, where I'm discussing about the liquid phase exfoliation, here you are actually peeling off the bulk material. Okay, or what you call, you do have a bulk material, and layer by layer you need to peel it. Okay, and that can be done either mechanically, ball milling, chemical exfoliation, electrochemical exfoliation, or liquid phase exfoliation. Sorry. So mechanical exfoliation, as the name implies, here you can use any tools like rollers or something like that, where in which the mechanical force is being applied onto the layers, and that's how that the layer is being peeled off from the parent atom, not parent atom, parent material. And when it comes to ball milling, you might know that the ceramic balls are being utilized inside one particular rolling tank or container, where you will allow this the material to get accumulated and it's being rolled. And that's how the material is being peeled, and where how you can get the 2D material. And then comes the chemical exfoliation and electrochemical exfoliation. There, what happens is that intercalation as well as what do you call that bursting or cavitation, the so-called cavitation happens. So intercalation and cavitation occurs in chemical and electrochemical exfoliation, where intercalation is nothing but this liquid will get into the spaces of this bulk material. Okay, and then what happens is that minor bubbles will form, and then it explodes. That will lead to that so-called exfoliation. So I will show you how it actually happens. The same happens with the liquid phase exfoliation too. But here in liquid phase exfoliation, this is the point I want to stress too much, a bit more. Like, see, liquid phase exfoliation, you are not actually carrying out any chemical exfoliation, or you are not actually using any current or something to, initiate these kind of peeling. Here, what you're using is that, as you might know, that we use a probe sonicator, and we need a medium, liquid medium. Okay, so that solvent and this particulates what you need to peel off. You need to take in that particular medium, and then you will ultrasonicate it, and that ultrasonication will give you the so-called exfoliation. So by saying this, you might be a bit puzzled, like how it can be carried out. So I will just show you that the physics when it comes to a bit more deeper into that particular topic. So why liquid phase exfoliation is prepared? I mean preferred. Why this liquid phase exfoliation preferred? You can see that in top-down approaches, you have many exfoliation technique. I told that mechanical, ball milling, chemical, UALP, or ultrasonication assisted liquid phase exfoliation can be employed. But you can here see that the optimum output is being given by UALP or ultrasonication assisted liquid phase exfoliation, or the exfoliation in which the ultrasonication and the liquid is helping you to carry out what exfoliation. So that method is actually giving you comparatively higher yield, less cost, scalability, better scalability, and better what structural integrity, or the damage is being produced, or you can see minimal damage. See, these are the parameters you always need to look onto when you are actually synthesizing the nanoparticles. So this technique is giving you the maximum output. So that's the reason why we or the researchers or want to actually insist on to this particular technique. Okay, so this is the ultrasonication assisted liquid phase exfoliation. So just take a look onto how this process carry out. So this is the bulk powder. Okay, first you will take it into the solvent where it is being ultrasonicated. Okay, the ultrasonicator is nothing but it's a prop sonicator which will give that ultrasonic sound waves, and this sound waves will help in exfoliation. I will show you the physics later. So this ultrasonication will lead to exfoliation, and once it has been exfoliated, now you cannot directly take the entire fluid or the entire solvents for the next set of characterization. You need to do centrifugation. So you need to centrifuge it, and then you need to take the supernatant of it. You need to discard the bulk deposit that has been deposited at the bottom, and you need to take the supernatant. And in that supernatant, we have got what the exfoliated 2D material, whatever. It could be graphene, it could be SPN, whatever. So as we are having that 2D material inside the supernatant, we need to dry it. Okay, that's the only source by which you can actually take out this HBN and sorry, the nanoparticles or the two-dimensional nanoparticles. So by drying it, you can get what nano sheets. Now I call it as what nano sheets, not the nanoparticle. Okay, so nano sheets or the so-called bulk nanoparticle is being brought down to nano sheets where its nanometric length or the nanometric dimension is being brought below 100 nanometer. Okay, so this is the physics behind the ultrasonication. This is what happens when you actually ultrasonicate the particulates inside the solvent. Okay, so when the particle is being kept inside the solvent and when the prop sonication is being carried out, so you know that this ultrasonic sound or ultrasound sound waves will create tiny bubbles inside it. Okay, and these bubbles, the bubble do have a tendency to grow, right? Because inside which there will be air, and this will grow, and literally it will, at a point, it will burst out. Okay, so these things happens, after intercalation. The intercalation is nothing but, see, these were the stacked layers. So once I put this bulk material into the solvent, these the so-called solvent will get into the layers of these stacked layers. Okay, and the bubbles also does the same. And this bubble will grow and it sputters, or the so-called bubble collapse happens between these layers. And that what the collapse or the sudden collapse is called cavitation. That process itself is called cavitation, and that cavitation will lead to what? Will lead to the exfoliation. Okay, that will lead to the exfoliation, and that causes these layers to separate from each other. Okay, so when you choose the solvent, you make sure that those solvents do possess the same surface energy, sorry, the same energy or as that of the your exfoliating material. So that is very necessary because in our research we took hexagonal boron nitride bulk material. why we chose the isopropanol as the optimal solvent for HBN. So what are the parameters influencing the exfoliations? As you know, that exfoliation is nothing but peeling down or peeling of this material. So there are several factors that actually govern the exfoliation, and they are sonication power, sonication time, frequency, temperature, centrifugation time, centrifugation speed, initial concentration, solvent selection. Solvent selection, I already mentioned. We need to have the surface energy matching with that of material. Okay, now to the power, time, frequency. What is the power, time, and frequency? So power, time, and frequency is nothing but this probe sonicator is actually nothing but it is generating this ultrasonic sound, right? So that vibration power or the power that is being given by the instrument should be kept in a way that it should be optimum. It should not be too high. It should not be too low. Likewise, you need to keep it. So you might be having an, then what is the optimum power? That can be only be found out by doing certain experiments. So in prop sonicator, the power ranges from 110, 220, 330, 440, 550. Likewise, it goes. Okay, till 550 it is there. Then the instrument, the normal instrument, normal desktop instrument is having till 550 watts. So you can actually change those sonication power, okay, and find out which is giving you the maximum exfoliated thing. How you will actually find out what is the maximum exfoliated thing means you need to find out the yield. That means if you have taken 100 milligrams of bulk HBN or bulk nanoparticle, okay, how much exfoliated material you got after exfoliation, or how much milligrams of exfoliated powder you got after exfoliation. So that will give you what the yield. Okay, so likewise, time frequency also need to be what controlled. So and that you can see that normally you need to keep it in a longer time and as well as higher temperature. Why I opted, not why I opted, this is the normal thing is that you need to always keep it in a higher temperature level. The reason is that, when you actually increases the temperature, the solvent temperature, as you increase the solvent temperature, its viscosity also reduces. Okay. So when you reduce a solvent viscosity, it will be easier the particles to be exfoliated, or else it's very difficult for it to get exfoliated and get well dispersed within the system. So it's always better to do this, to lower down the solvent viscosity. Yes, so the centrifugation time is also a factor. You need to do a longer time centrifugation. Yes, and optimum centrifugation speed as well. So after carrying out these exfoliation, it's very important for you to do the characterization techniques. Characterization techniques is nothing but, you might be doing the synthesis of two-dimensional nanoparticles. Okay, it could be bottom-up approach, it could be top-down approach, and whatever may be the approach you used, finally you are going to get one particle. Okay, how will you validate that the particle you obtained or you got is the one you are actually aiming at? So you have several characterization techniques by which you can actually validate those things. So in case of two-dimensional nanoparticle synthesis, you can rely on these kind of characterization techniques: UV visible spectroscopy, transmission electron microscopy, field emission scan electron microscopy, X-ray diffraction, Raman spectroscopy, Fourier transform infrared spectroscopy, and X-ray photospectroscopy. So each and every characterization do have a function. Okay, so see, UV definitely will give you an yield estimation. Yield estimation is very relevant thing, and not only that, the particles what you are getting, no, and those particles band gap can be found out with the help of UV visible spectroscopy, because you need to plot the talk plot, and from that talk plot, that means the indirect band gap plotting, you can find out whether you got the correct particle what you are aiming at. For example, if you have actually exfoliated HBN, hexagonal boron nitride, and you actually exfoliated to hexagonal boron nitride nanosheet. Okay, so the electron volt or the so-called EV band of that HBN is nearly 5.2. And the HBNNS is getting nearly to 5.2 means, yes, what you have done is right. Its structural integrity or the so-called the structure is being maintained. And you have made sure that the band gap is being kept intact. Okay, so likewise, TEM is used for finding out the number of layers because in bulk material, when you visualize the bulk material with the TEM, as this is a transmission electron microscopy, it will appear as an opaque structure. But when you keep this, single layered HBNNS or single layered graphene, you can see more, transparent kind of images. So by that, you can predict that the number of layers has been reduced, and you can actually count down the layers as well. Yeah. So FSM is definitely used for morphology analysis, you might know, and crystal structure. Raman is used for the structural defect finding out. So these are the several characterizations. I don't want to go deep into it. So these are the techniques by which you can actually found out whether the materials or the synthesized material is, what you are aiming at or not. So now I want to emphasize what was or what is the role of machine learning in nanomaterials. See, for example, if you need to do this exfoliation, okay, and as I said, there are several parameters like power, time, and the solvent. Selection is very critical in finding out or to get the yield. And you done an experiment with one particular input parameter, like you chose ethanol as your solvent, you kept it 220 as your ultrasonication power, you kept this ultrasonication time, okay, not 30 minutes. So these were your input parameters. And you found out that the yield was like 10 mg. From 100 mg, you got 10 mg. 10% was the yield parameter, or the yield percentage. See, if I'm asking you, what is the optimum, combination of your input parameter that will give you the maximum yield, then what you need to actually do? If you are relying on traditional approach means you need to do n number of experiments to find out which will give you the optimum yield percentage. So if you are relying on AI approach, where you need to definitely do some experimental trials with which you can multiply your data with AI, for example, data augmentation without actually without creating any sorts of changes in the matter. And changes in the matter in sense it's not any causing any integral issues. And with that, if you can bring up a greater number of data sets, and with that you can actually predict the optimum parameter with which you can give or with which you can get the maximum yield. So definitely you need to rely on those machine learning in nanomaterial. So you got several algorithms like linear regression, random forest, several other kind of these ML algorithms are there. You can rely on this, and you can actually can get better yield percentage or prediction can be carried out with these machine learning. So what I want to tell you is that you can rely on machine learning to minimize the experimental trials. Okay. So what is the major challenges in ultrasonication assisted liquid phase exfoliation? Even though this is giving you, better outcomes, there are several factors, okay, or there are major challenges. You can see that it is giving, low exfoliation yield at times. Okay, why I'm telling is that, if you're depending on chemical exfoliation, you might get a bit more, two-dimensional outputs. But the thing is that structural integrity and cost-wise, it is at the upper hand in the case of chemical exfoliation. So you cannot actually rely on to it for a longer time. But still, This ultrasonication assisted liquid phase exfoliation, this is one challenge, low exfoliation yield in certain cases, and restacking of nanosheets. Restacking means reagglomeration happens, and solvent incompatibility. That's why I said that always choose the solvent that has the energy similar to the surface energy of the nanoparticle. And there are certain cases in which, due to excessive sonication, structural damage could happen. So that's why I told that you need to make sure that the ultrasonication power, the ultrasonication time should be optimized. If you are not optimizing it, it could lead to a situation where it could structurally damage it. What I'm telling is structurally damaged means it can defect your atomic structure as well. It's not the peripheral damage. I'm talking about the structure as well, the atomic structure as well. So you need to take care about the sonication parameters while you do the ultrasonication as step liquid phase exfoliations. And scale up is another challenge. Scale up means if you want to extract a larger number of two-dimensional nanosheets from this using UALP, this is a bit challenging thing because once you need to optimize it, and then only you can actually find out the optimized characteristics, and then only you can actually go ahead with the scale up, procedures. So yeah, so the current research trends in two-dimensional nanomaterial exfoliation. So this is very important. The faculties who are actually planning for the research in two-dimensional nanomaterial and specifically in exfoliation, you can take a look onto these things. Researchers are actually right now focusing onto the green solvents. Green solvents are those solvents that doesn't, have a harmful effect onto the environment, definitely. And those solvents you can rely on to, and even you can think about the co-solvents, where you can think about the combination of one or two solvents and how it affects the exfoliation. Then you can think about surfactant assisted one, polymer assisted one, surface functionalization, then AI assisted optimization, then sustainable production. So these are, the areas where researchers are currently focusing on to. So you can really take a look onto this thing and how you can actually approach the so-called exfoliation, or the roadmap is being shown over here, where that is already mentioned earlier, like bulk to few layer nanosheets by UALP. You can think about the green solvents, where in which those green solvents helps in exfoliation. And one more thing, what I want to stress is functionalization. See, functionalization means you just think about some kind of surfactant or any physical or chemical functionalization over the surface of these nanoparticles, such that after exfoliation or after getting into that nanosheet stage, you can modify the surface and make it more make it more adjustable, or make it more ready for the dispersion. Okay, even though, as I earlier said, that even though you are making it to nanosheet now, there are chances for reagglomeration. So if there is any chance, means you better go ahead with the functionalization, because functionalization means you are just allowing another chemical to deposit over your nanoparticle, thus causing, or thus actually you are blocking your another nanoparticle or another nanosheet adhesion to it. So it will act as a intermediate surface that actually, decline the trend of attraction. So thus way you can actually plan for this your functionalization, or which will actually help you in dispersion as well. Then definitely the machine learning technologies, where in which you can employ that for to find out the yield percentage and so on like that. So these are the trends, the research trends, and several parameters or several, elements that you can actually look into, and specifically in the area of exfoliation of 2D nanomaterial. So where you can apply this exfoliated two-dimensional nanomaterials. So you can just go through it. It's, polymer nanocomposite preparations. You can definitely utilize this exfoliated nanomaterials, where because the reason is that it improves it mechanically. like thermal stability, it gives durability. Then aerospace structures, thermal interfaces, flexible electronics, energy storage, EMI shielding, sensors, biomedical applications, hydrogen storage, water purification, everywhere actually. It is actually contributing to sustainable factors as well as the major, application sectors. So definitely there is a good chance, to for the researchers to take up this particular section where you can actually find it befitting for many other applications, emerging applications, I should say. So there are certain gaps. Definitely, there are certain gaps, and the challenges, as I have already mentioned, and how you can actually you can employ your research and you can make it more soothing for your particular career or the so-called research field. See, we had several challenges like a low exfoliation yield, non-optimized ultrasonication parameter was there, lack of solvent selections, universal time-consuming trial and error optimization, limited predictive modeling. So these were the traditional shortcomings we were having. So what you can actually propose is that you need to optimize the ultrasonication parameter. Like I said, you actually tune the optimization parameter like time, power, and the solvent you are using. Thus, by optimizing it, you can have the better yield. Okay, so by doing that, definitely you can improve the exfoliation yield. And once you got the better exfoliation yield, it's not just the amount you're getting, it's the quality of nano sheets you are getting that matters much. Okay, so in order to make sure that you are getting the perfect nano sheet or the high quality nano sheet, you need to characterize the nano sheet comprehensively. What I've stressed comprehensively means you need to take the nano sheets to several characterization tools and make sure that its structural, chemical, morphological characteristics are not altered in exfoliation. So once it is been, made sure, means whatever you have done is perfect. Okay, you can go ahead with this particular direction. Then definitely, then comes the AI model where you can have predictive AI models to find out which combination will give you the maximum yield percentage, just to find out the yield percentage and the crystal or crystal structure integrity likewise. So thereby utilizing these predictive AI models, you can reduce the experimental workload as well. So, by actually understanding these things, we actually ended up in the ultrasonication assisted exfoliation of hexagonal boron nitride. And this was the reason behind why I choose hexagonal boron nitride as my material and definitely the 2D material for the further research. And during my research, I have taken this HPN and I have done this, exfoliation of it. So there are many, still there are areas you can do the exfoliation as well. You can see graphene, MOS2, tungsten disulfide. You can think about the various solvents or ultrasonication parameters, whatever. So yes, in my case study, what I've done, or my research, what I've done is that I've taken the hexagonal boron nitride and I was trying to exfoliate it. So definitely the major point was that which solvent system I should take, or which will be giving me the maximum exfoliation yield, which ultrasonication power and time will give me the best yield, or what power and time I should fix, and which characterization techniques are important to find out successful exfoliation, and machine learning, whether it could fit well into in this particular scenario. So these were the research questions I was having, like, and that's how I ended up in doing this thing. So this was the methodology workflow I had, where I bulk HPN was taken to the solvent and ultrasonicated it. And after ultrasonication, I had centrifugation twice, actually, in lower RPM and higher RPM. And then I dried it and then found out the yield percentage. As I said, yield percentage is nothing but you are having a initial weight percentage And then after doing these steps of ultrasonication centrifugation, you will be getting the HBNNS and take the weight of it, and the fraction or the final by initial will give you the yield percentage. Okay, so that is actually the yield percentage, and I have done the characterization. Okay, to make sure that the obtained HBNNS do have the structural, morphological, and the other integrity. With integrity means it is at par with the same as that of the bulk HBN. And yes, I've done the parameter optimization where power, time, and solvent systems were altered, and comprehensive characterization was carried out. Different machine learning models were done, and after that, so this is, I'll tell you the final yield later. You just take a look onto the supernatant I got. Normally, this HBN is a white powder-like thing. So, after two-stage centrifugation, it looks like this. You are not supposed to take the bulk amount or the bulk particle, just the supernatant. And after that, the supernatant is being collected in a so-called dish, and I have dried it. So after drying, you will get what you will get that particles, and I'll weigh it and see. This is the yeah. Take a look onto this slide. You can see that yield percentage. Okay, so you can see that 16 trials, 16 experimental trials were done. Okay, so first I have taken isopropanol as my solvent. The reason is that isopropanol was having the similar energy, surface energy as that of hexagonal boron nitride. Okay, so I have used that isopropanol as my solvent, and I've carried out the ultrasonication at the power 330. Ultrasonication time was fixed at 45 minutes, and I've got yield percentage 9.97. Okay, then I thought of changing the time. Okay, in another experimental trial, I've changed the time to 90 minutes. I've got 11 percentage. I've changed the time to 135. I got 7.64. Then I thought of changing the power, and with a different timing, I got these yield percentage. Okay. Then I took another solvent, ethanol, with 330 ultrasonication power. See, at this stage, I tried to optimize the power. I tried to optimize the power because I analyzed the thing, and I found out that this 330 watts is giving me the maximum yield percentage. So we took the 330 as optimized power, then did the further experimentation with 45, 90, and 135 ultrasonication time, and I got these as the yield percentage. You can see that it is very low. So I understood that incorporating ethanol as a solvent won't give you better yield percentage. So I've used the isopropanol for my further study, where I've prepared the co-solvent in this ratio, 1:3, 1:1, 3:1. Yeah, and have taken ethanol just to have a reference. That's it. So 1:3, 1:1, and 3:1. So you can see that IPA DI water 1:1 gave me the highest yield percentage. Okay, so this was my actually experimental trials where I've changed the ultrasonication power, ultrasonication time, and have got several yield percentage. Okay, so similarly, you can see that this is the UV visual spectroscopy, and these peaks will give you nothing but it will give you the plots where in which you can actually find out the band gap of each HBNNS you got for each trials, and the size of the nanoparticles and even can be predicted. And this is the transmission electron microscopy analysis. ABC. See, this is the bulk HBN. And here you can see the exfoliated HBNNS. Okay, so right now you'll be having a doubt. So bulk HBN, yes, we understood. But what about this HBNNS? This HBNNS was extracted from my optimized power, time, as well as the solvent system. Okay, so my IPA assisted one, which gave me the maximum yield percentage. So that particular combination was taken, and that gave me the 12 percentage of yield. No, so I extracted HBN from it, and then I have done characterization. So take a look onto this transmission electron microscopy images. You can see that SBN is so opaque, and you cannot actually see the layers even. So here you can see that layers are very visible, and it's been brought down to minimal. And this is a selected area electron diffraction. And this will give you an idea of a single crystallinity or multiple crystallinity of the material. And definitely comes the HR term. HR term of the material is very important to find out the d-spacing of the material. Here you can see that the d-spacing of bulk HBN is 0.341, and the d-spacing of the hexagonal boron nitride nano sheets or the exfoliated one is showing about 0.346. That means that so-called exfoliation is effectively carried out. That's what we can say. And even not only this can actually tell you it is being effectively carried out. I'm telling you that much of that structural integrity is being carried out. There is no such what do you call defects in the so-called crystallinity. Okay, and here you can see that this is another image, field emission scanning electron microscopy, in which bulk thickness you can see where HBN is just the bulk HBN, and you can see that 52 nanometer, 75 nanometer, 78 nanometer, these were the thickness before exfoliation. And it was brought down to 40 nanometer, 19 nanometer. That means effective exfoliation was carried out. Okay, so this is the XRD spectroscopy. See, this will give you an idea that whether the crystal structure or atomic structure was preserved. Okay, so this black one is bulk HBN spectroscopy or XRD spectroscopy. You can see that at 26.93, a sharp peak where it's actually indicate the 002 plane, and nearly to that peak, or nearly to that 26.9 itself, HBNNS is showing. Okay, the 002 plane. So only 0.1 difference is showing between SBNNS and bulk HBN. So that itself is proving that the synthesized HBNNS has preserved the crystallinity or preserved the crystal structure, even though it was synthesized with a particular method. So this kind of validation is very important, because you need to compare with the bulk HBN, or you need to compare with the bulk form and the exfoliated, and make sure that those are aligning with the values. Okay, but there is another thing. You can see that peak intensity is different. Okay, peak intensity is different and the peak width is different. So FWHM, or full width half maximum, is increased in the case of what HBNNS. So that is another, another indication of exfoliation. Okay, so while exfoliating the particles, the FWHM will improve. Okay, the peak intensity will decrease, the FWHM will improve. So this is another, important thing that you can visualize when you actually exfoliate it, specifically in XRD. And see, this is another area where I have done a comparison between the bulk HB and exfoliated HB. And take a look onto the 2 theta angle, planes of bulk HB and exfoliated HB. See, as I said already, the 2 theta value is somewhat near to the bulk form. That means here you can see the 2 theta value of the exfoliated, and they are, very well, aligned with the values of the bulk HBN. And here comes our next parameters. Full width half maximum, you can see that it is improved. Yes, while exfoliating, it is increased. Each planes, you can check onto each plane. In every Miller indices or in every atomic planes, this FWHM is improved. And d-spacing is also improved. And as you are exfoliating it, the crystallite size should be minimized. Okay, crystallite size you can find out by the equation, Scherrer equation, D is equal to K lambda theta cos theta. Okay, so with that you can find out Scherrer equation, and definitely you can get the d-spacing as well with the help of Bragg's equation n lambda 2d sine theta. So likewise, you need to find out each values, and you need to compare these two elements or two nanoparticles, specifically the bulk and exfoliated HBN, and you need to make a plot, not make a plot. You need to give an inference that how how you can say that it is exfoliated, keeping the integrity in the case of what crystallinity and atomic structure. Okay, so again, I want to tell that the d-spacing is being improved, FWHM is being improved, and crystallite size is decreased. So these are the important parameter you can visualize while exfoliation, which can be seen in XRD outcomes. So this is FTIR and Raman spectroscopy. Again, FTIR is being carried out to find out the functional groups. And you can see that bulk HBN and HBNNS having the same functional groups. There is no change in it. And definitely there is no crystal damage that occurred during synthesis of HBNNS. It is very evident. See, 1367, it is closely lying near to it. And by comparing the ratio of D and G bands, you can say that there is no such defect happening within the atomic structure. So this is again, I have consolidated the XRD values, the TEM values, and FESM values. Why is that in TEM you can get the d-spacing. I have already shown you a TEM image, no, where in HR-TEM, high resolution transmission electron microscopy image, you will get the TEM value. Okay. And I have compared it with the d-spacing I have got from XRD. Okay. Here you can see that it is very well, near to the experimental value. So it is very much near to the experimental value, or you can see that it is somewhat compromising. And this way you can actually have a look onto what you have done as experimentation, and what you have got in several other characterization techniques. And see, this is the nanosheet thickness in bulk HBN and SPNNS, and this will give you an idea that the crystallinity or the structural damage is not there in the system. And in that particular case study, or in that particular in our research work, we have employed this ML algorithms as well as DL algorithms for prediction. And this is the actually prediction or the workflow of it, where you might know that ML is a system in which they will carry out the training, and then it will give you prediction. Okay, so that trained model, we need to again feed in the combination of parameters, which will give you an yield prediction. So the same happens with the DL structure as well. And yeah, so that's how you will get the prediction. So these are the parameters, or the so-called different models. And you can see that MAP, or this is the mean absolute percentage error. Okay, so this is actually a performance parameter of this model. And you need to get the minimal of percentage error, or the error, to say that the particular model is better for that particular so-called yield prediction. And I have used several machine learning models as well as deep learning models for its prediction. And I could say that deep neural network, or the with Adam optimizer, give me the better results. And see, and it is very evident over here. You can see that deep neural network Adam optimizer with the learning rate 0.01 is having 0.08. And when it comes to 0.001, it is coming nearer to 0.02, which is very less than that of the other algorithm models. So these are the R-square values I've got. And this is perfectly for this here. I have only used the yield percentage prediction, but I've taken the values, experimental values, and the predicted values, and have plotted and found out the R-square value. So this is just the inference what I've got for the several machine learning and deep learning models. In short, I can say that comparing with the machine learning models, deep learning models gave me the better results because the so-called deep learning is being carried out, and they have given me the minimal errors that gave me the better R-square value. So the research conclusion, or what I've done with HBNNS, I found out that the optimal exfoliation parameters were 330 watts. Okay, as I have said earlier, 330 watts was the better result I have got, and which gave me the better result. 90 minutes was the optimum ultrasonication time, and IPA day water combination was 1:1. So this combination of 330, 90 minutes, 1:1 was the best combination that gave me the better result. And I have used several characterization techniques. I already told you for to finding out, the structural integrity, chemical integrity, and the morphological, uniqueness, etc. And I've done, machine learning analysis where DNN with Adam Optimizer gave me the better result. And we were able to publish our paper in Q1 Jan itself. See, why I kept this research, our case study, no, our research as a case study is that I was just showing you how I was able to exfoliate HBN, okay, effectively exfoliate HBN and able to publish that in a Q1 journal. Or the reason is that these combination or these changes in solvents, these changes in optimization, I mean, these changes in parameters will help you to get a yield and will help you to get a high quality nano sheets, which can be utilized for several applications. Okay, this particular nanoparticle can be utilized for several applications. HPN itself can be used for thermal as well as structural particles or structural applications. So what I want to tell you is that you need to utilize several nanoparticles. Like I said, 2D materials are still there. Graphene, MOS2 is there, tungsten disulfide is there. You can use n number of methods, n number of top-down approaches there, n number of bottom-up approaches there. You can actually optimize the several kind of parameters in which you can actually get a better nanoparticles. And see, it's not just producing nanoparticles, it's just producing high quality nanoparticles. What is high quality nanoparticles means without changing its structural integrity, without changing its chemical integrity, you need to produce materials. So yes, you can actually think about that. You can do research on that particular thing. So these are the major key takeaways where these two-dimensional nanomaterials give you exceptional mechanical, thermal, and electrical surface properties. Definitely, as I said, this can be utilized for several applications. Notable several applications you can take. And the only thing is that you need to do the exfoliations or the so-called surface functionalization that is fitting the application. Okay, functionalization is very important, but it should fit the applications. Chemical functionalization should be done in a way that that chemical should go along with your applications. Okay, then definitely you need to learn about, or you need to have an idea about the characterizations. Sorry to say learning, everyone is learning. And definitely you need to have an idea, or you need obtained nanoparticles is what you are aiming at, like nanoparticle or nanosheet is as the same as that you were having at the initial itself. So those defects should not be occurred. And in order to validate it, you need to undergo several characterization techniques. So try to use these kind of characterization techniques. Then optimizations, and you need to go forward with the process optimizations. And this process optimization, I am talking about the UALP only, where you can think about solvent selection. Still, there are areas like you can think about a sustainable solution, you can think about green solutions, where it will give you the maximum, yield percentage and high quality sheets. And artificial intelligence, definitely, it's an era of artificial intelligence where you can think about learning, machine learning and deep learning models, which can give you or which can predict, exploration leads, yields. And yes, and the future perspective is nothing but, integration of this processing, material characterization, AI intelligence, and functional nanomaterials, material synthesis. Okay, you should not limit yourself in synthesizing nanoparticles, as such. Even in our research, we have incorporated in in nano, polymers, Uh, so likewise, you need to think about the area where you can utilize the particular two-dimensional nano sheets. And why I'm telling is that this is this has got immense, immense what do you call throw in that particular thing. That means as it is having the surface area, more surface area, so it do have that benefit of giving to a larger area, and you can improve the reinforcement, you can improve the structural or not structural, you can improve other properties as well. So always two-dimensional materials contribute a greater share in these kind of property enhancement techniques. So I have mentioned about the research possibilities as well in over here, where you can think about the novel solvent, definitely, and wider range of 2D materials. I have mentioned one case study where we have used HBN. You can think about more nanoparticles, and definitely AIML incorporations, and the application models. Definitely, the wherever you want to fit in this particular material is the the basic question. So you need to think about that. You can think about the nano particle composite materials that can serve as a best material for that particular application. So definitely, we all are moving towards a sustainable society, where in which you need to think about the sustainable metrics, sustainable particles, and likewise, you can have a lot of research possibilities ahead. And yeah, so that's all about exfoliation. And why I wanted to tell you about this thing is that this do have, or the two-dimensional nanoparticle is is a particular area where a lot of research is happening. And I thought of giving a small spark in that particular area so that you can also take up research in that particular area and do a lot of work in that particular area. And yes, let it happen. And that's all. Thank you.
Uh, Thank you, Jerrin. So,
Thank you, sir. Thank you, sir.
participants, if you have any doubt, you can ask. Before that, I think I don't know if I missed anywhere. There was some network issue. So, uh, you told that the yield is very low for this exfoliation.
Yeah, yeah.
What will be the we can uh, the quality of product that we are getting? We can also purchase the same product, from the market. So, what will be the gap in the cost if we are exfoliating or if we are purchasing the same product with same quality?
Sorry, I didn't get you. Can you once again say it?
So, after exfoliation, we will get some products.
Yeah, 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 yeah,
The same quality product is available in the market. If it
yeah.
is available, how much will be the difference in cost that we have?
Yeah, 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 yeah. Yeah, understood, understood. See, for example, in the case of hexanyl boron nitrate nanoparticle, I want to emphasize in that one because we were doing in that particular thing. You will get bulk HBN. For sure, you will get bulk HBN. For 100 grams, it is costing around, not 100 grams, 25 grams, it is costing around 12,000 rupees. Okay. So the challenge is that you cannot take that HBN as such for your synthesis or the further. nanocomposite preparation. Okay, so there you need to always convert it into nano sheet. If you're not converting it into nano sheet means it won't contribute much to the strength. I mean, strength in sense, the structural strength, the thermal strength, or whatever the so-called electrical parameters, if you want to improve, means you need to definitely exfoliate it. And if you are planning to buy an exfoliated material, even if you try to buy it, you won't get it because exfoliated material won't exist as such for a long period of time because there is always a tendency for it to again get reagglomerated. Reagglomerated. Okay. So always you need to make sure that it is not happening within the system. So, that's the reason why you are not getting that exfoliated materials in market. Okay. And specifically in the case of 2D materials, nano sheet as such, you won't get in the market. The thing is that there are again chances of it in to get reagglomerated, or else you need to surface functionalize it. So again, the question comes, then what will we do to avoid this thing? You need to surface functionalize it. See, surface functionalization is always, depending on what kind of application you are going to use it. Like, for example, if you are going to use it for a structural integrity, you can definitely go ahead with the chemical exfoliation, not chemical functionalization, or even physical functionalization is fine. But it all depends on what particular chemical you are utilizing it, because it should not disintegrate or it should not cause a ill effect to the entire composite. So that's the reason why we are not having the nano sheet as such, and they cannot even functionalize it because for each particular application, each chemical is required. So that is a major challenge in it.
Okay, thank you. So, any other participants, if you have any doubt, you can ask.
Yeah. Yeah. Am I audible?
Yeah, you are audible, sir.
Thank you, Dr. Varughese. So your slides are very good, very
Thank you,
appealing.
sir. Thank you.
Actually, only thing is that you can increase the
Got it.
yeah. Otherwise,
Okay, sir.
slides are very good. Actually,
Okay,
I
sir.
have a small doubts
Yes,
in the
sir.
application exfoliation.
Yes, sir.
Because they are in many cases your fine I observe that your yield is very low.
Yes, sir.
Yeah, I think lesser than 20%.
Yeah.
So that means wastage is very high in that case.
Yeah,
Can
yeah.
you say like
Correct.
this? Wastage is very high. Actually,
Yeah,
what
yeah, yeah.
about the wastage? Where does it go during
Sir, yeah,
ultrasonic?
I'll tell you. Yeah, see, you can even think about a usage of that particular deposits. For example, once you do the centrifugation, no, the deposits, what you're getting is nothing but the bulk material itself. Okay,
Yes.
so you can again use it and again ultrasonicate it, and further you can extract it. Okay, so this is actually what I have got the result is actually one time use. I've only taken one time, and that's how the yield is coming a bit low. Okay, so there is again a chance for you to take that deposit or the sediment. We call it as bulk HBN, and again you can do that so-called what you call ultrasonication and further centrifugation, where you can maximum extract from the system. But the thing is that it is a bit time-consuming one because in the second stage you won't get that much of a percentage. It declines actually. So there is another issue in that thing, but still you can maximum extract from that particular system.
Yeah. Yes. Then another thing you mentioned about that ultrasonication.
Yes,
Do
sir.
you have any image of that instrument? What is the price of that equipment in the market?
Price of the equipment will come around 1.5 lakh, sir. Nearly 1.5 lakh.
Oh, not much. Not much.
Yeah. Not much. And you cannot use that what do you call normal what do you call bat sonicator. Bat sonicator you cannot use. You can only use this prop sonicator for this ultrasonication. Because people used to ask me whether it is possible to use a bath sonicator for
Mhm.
ultrasonication, as I said,
Mhm.
exfoliation. But
Yes, yes.
exfoliation, it is very difficult to use a bath sonicator. Definitely, you need to go ahead with the prop sonicator. And for an average or a decent ultrasonicator, it will cost around 1.2 to 1.5 lakhs, sir. Hello.
Hello. Ah, hello.
Yes, sir.
Yeah, I think
Hello.
there was some network problem. Actually, I could not hear your lines.
Oh, I see. I see.
Yeah, yeah.
Shall I repeat, sir? Shall I repeat
Ah,
once more?
yes, yes. Yeah, it will be great if you repeat
Yeah,
those
yeah,
lines.
yeah. The ultrasonicator, na,
Yes.
best thing is to use the prop sonicator. Prop sonicator. You should
Okay.
not use a bath sonicator. Bath
Yes.
sonicator, it won't generate that much of power. Okay,
Mhm.
it's always better to use prop sonicator, and that will cost around 1.2 to 1.5.
Okay.
I can share you the image, sir. Right now in my slide, I don't have that image. I can later share it with you
Yes.
through Umanath, sir. I'll definitely share it with you.
Mhm. And in many cases, when you go for nanoparticles or whatever, because you use 2D sheets, right?
Yeah, yeah,
The
yeah. Yeah,
one
yeah.
problem.
The exfoliation, see, for example, in my case, I have actually prepared nano composite. Okay, so
Right.
what I've done is that I have extracted this supernatant. Okay, in that supernatant, for actually finding out this was the best optimized parameter, I've utilized those experimental trials. And when I am into the nano composite preparation, no, I will not ever do the what do you call drying process, because if you are
Mhm.
going ahead with the drying process, it will definitely again reagglomerate.
Correct.
So within that solvent itself, I'll try to add my metrics, and then I will go with the again the ultrasonication, and then I'll try to remove the solvent. That's the only thing what you can do, to avoid the reagglomeration. Or else you need to go ahead with the what you call modification. Chemical modification you can carry out so
Yes.
that that surface energy is being altered. Because see, the surface energy, as the surface energy is the same, they again have that tendency to reagglomerate. That van der Waals force is there always, to come in contact with each other and to bind them together. So when you are actually applying another layer over onto this particular 2D material, it acts as a boundary. It acts as a layer, that will doesn't allow this another particle to come and stick over to this particular modified layer, because they share different energies.
You mean orientation? Is it different, or you use a separate type of thing?
Not orientation, sir. See, what I'm telling is we are trying to, if we are doing a chemical modification, no,
Yes.
one additional chemical is coming and coating over the surface.
Okay.
So
I
once you
get
are
it.
used, yeah, yeah. So once you are coating, it means na, it won't again
Mhm.
come and try to get contact with the surface, because these two chemicals are having, see, HBN is having one particular surface energy, and the chemical, for example, if I am used selenization compound, okay. So if that is a selenization compound I have coated over the HBN, means that selenization compound is having another surface energy. So definitely there is no point in van der Waals energy that comes in between to get adhesion. So that can be reduced to a greater extent.
Hello.
Hello.
Yes.
Yeah,
Actually,
yes, sir.
I
Yes.
have some network issues. That is
Oh, I
causing
see.
problem.
Okay,
Actually,
sir.
thank you very much. Actually, another question is there. If you go to
Yeah,
the
yeah.
slide number 25,
Yeah, sir.
that you have shown that crystallized size.
One
Yeah,
second, sir.
yeah. Just go to that one query is there.
1 second, sir. Good. 25, no? Yeah,
25.
sir.
Yeah.
Yeah, sir. Tell me, sir.
No, I think in my laptop it is not visible.
Oh, I see. Uh, I have
Yeah.
actually
Yes.
made that
Now it
25th
is.
slide. Yeah, yeah,
Yes.
yeah. Tell me, sir.
Yeah. Now it is visible. Now, in
Hmm.
case of bulk HBN, hexagonal
Yeah,
boron nitride, and
correct.
exfoliated, if you just look at this crystallized size,
Yeah.
let us take the first one when you
Hmm.
compare the 002 plane. So
Yeah,
it is 19.86, and on the other side it is 16.46. But
correct.
in case of you call it bulk, and when you call it 2D nano,
Hmm.
there are not. When you go look at the size difference, no, that is not high.
Hmm.
You are not getting very.
See, sir, what I'm trying to say in that particular slide is that, when you exfoliate it, this crystallite size will reduce a bit. Crystallite size will reduce a bit because the thing is that this crystallite size computation, we use the FWHM as a coordinate, and as well as we take the theta value.
You can. It's actually, I could not get it again. That net.
Hello?
Yeah, now I am getting. A network issue is going on.
Yeah. Sir,
Yeah.
this crystallite size, for that
Mhm.
we actually take FWHM or a
Yes,
full width,
FWHL. Yes, full width at half
and
maximum. Yeah.
and this Bragg's angle. Okay,
Mm.
so what is that in this particular 002 plane itself? When we
Mhm.
take a look onto that, you can see that. Uh, I'll show you another one. You can see over
So the
here.
FWHM will be increasing when the size reduction will be going on.
Correct.
Yeah.
FWHM is increasing.
Yeah.
So when FWHM is increasing means that will affect the crystallite size as well. So that is the reason why we are getting that reduced size in the exfoliation.
No. My
So
question is that there is not drastic change in the crystallized size. Small.
small changes
Yeah.
there, small changes only there, sir. Like in this case, you can see around 3 nanometer only, not
3
much of.
nanometer.
Yeah.
But my question is that my query is that you call it.
Sir. Hello, sir. You are not audible, sir. Sir, you are not audible. Umanath, sir. Hello.
Yeah. Now it is audible. Yeah, coming.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Can you repeat, sir? I didn't hear you actually.
Yeah,
That's why.
actually, the network is going on.
Yeah.
Actually, when you call it bulk, that is
Yeah.
bulk is itself is nano actually. Now,
Ah.
because on the other side there is not
Oh,
much.
sir, I will tell you. Now I
Yes,
understood what you are asking.
yes.
Sir. This is actually the crystallite size, not
Crystallized.
the physical size.
Oh,
Okay.
you talk about
Phys-
the physical size in that case.
Sir, the physical size is too much. See, bulk
Ah,
HBN, it will come beyond the 200. I mean, not 200, nearly 70 nanometer. I'll show you one thing. So take a look here,
that
sir.
may be agglomerated, no? That may be
Yeah,
agglomerated.
yeah. 75 nanometer, 52 nanometer. These things will be around, these are called bulk HBN along with that agglomerated HBN.
I think
Definitely, as you said,
on the left hand side it is I think a backscattered image, and right hand side it is I think secondary electron image. Is it correct?
no, sir. This is
No.
FESM image only,
Uh, no. My
and
question is one maybe backscattered or it is secondary electron.
secondary electrons, sir.
Secondary electron. Okay.
Yeah. So both are having the same thing, but you can see that after exfoliation, that thickness is being brought down.
Aha.
Okay, but that physical thickness is reduced a greater extent. physical thickness is reduced a greater extent. Definitely for bulk HPN, there is, you can't actually peel out and then show that particular image. This is how we get it from the market. Okay, this is how we get it from the manufacturer, where you can get the bulk HBN size around 50 to 75. They actually give us the bulk HBN telling that, see, these are the nanometric, or these are the thickness we are having from right from 50 nanometer to 75 or 80 nanometer. And after exfoliation, you can see that it was brought around 40 nanometer, 14 to 19
Now
nanometer physical thickness.
I get it now. I get it.
Yeah. And but this was something related to crystallite size, sir. Okay, sir, I got it, sir. I got it.
Yeah,
Thank
yeah.
you, sir.
Thank you. Thank you. Thank you very much.
So, is there anyone else? Anyway, if you have any doubt and if you want to get some answers, I can share his contact details if you want, and you can contact him
And sir,
personally.
it's okay. Like if there is any doubt, means sir, you just take that questions and just mail to me. I'll
Yeah,
definitely
sure.
share the details, sir.
Sure.
And sir, thank you so much for inviting me. Once again, thank you so much for inviting me, and thank you for
Yeah.
being a part of this wonderful FDP. And thank you,
Yeah,
sir.
the pleasure is ours. So we were able to get some expert talk. So participants, with that, the 6-day FTP is coming to an end. I'm sure you have learned something new, and it has been fruitful for your future research or future journey. So I would like to thank Dr. Jerrin Joy Varughese for delivering session, and all other resource persons for being a part of this. And to the participants, we can give you distribute your certificate by Monday only. Please bear with us. And by Monday evening, I think we can distribute your certificates. So once again, thank you, Jerrin. And with that, we can stop the presentation, and I'll share the Google feedback form. Please fill it, and there will be an additional form for overall FDP, not the session. So please fill both forms. Thank you. Thank you, Jerrin.
Thank you, sir.